Hi guys. So what we're going to look at today is an application of what we did last class with transformations. So we're going to take what we learned about transformations and actually apply them to a new parent function. And this is something that you guys are going to see happen in most of the units that we do this year. So the first new parent function we're going to look at is the absolute value parent function. So the absolute value parent function is just the absolute value of x. And if you remember, absolute value is a number's distance from 0. So like the absolute value of 3 is 3, but the absolute value of negative 3 is also 3. So in order to see what this graph is going to look like, we're just going to pick some test points to plug in. I almost always start with 0, just to see what happens there. So the absolute value of 0 is 0. Absolute value of 1 is 1. 2 is 2. 3 is 3. Let's look at some negative numbers. Absolute value of negative 1 is 1. Absolute value of negative 2 is 2. And the absolute value of negative 3 is 3. So if I were to plot these points, you can probably see a pattern that's happening here. And this is one of the easiest shapes for most people to remember because absolute value looks like a V. So the domain of this graph is from negative infinity to infinity. And this is just reviewing all those characteristics we talked about the very first day. The range of this graph is from 0 to infinity. Again, it is a bracket at 0. This graph is increasing from 0 to infinity, decreasing from negative infinity to 0, positive from negative infinity to 0, and also from 0 to infinity. Remember, at 0, it's just 0. It's not really positive. It's not negative anywhere. For end behavior, we write two statements. As x approaches negative infinity and as x approaches positive infinity, f of x in both cases is approaching positive infinity. Symmetry is on the y-axis, so this is an even function. And then extrema, remember those are mins and maxes. This graph has both a relative and absolute minimum at the vertex. And in the parent function at 0, 0. All right, so now what we're going to look at is the transformations from last class. So if you remember, f of and any changes in the parentheses are horizontal changes. So just to recap, this was a shift right, a shift left, and then the b depended on the value. Okay, if b was greater than 1, it was a horizontal compression, and if b was in between 0 and 1, it was a horizontal stretch. And then if there's a negative in the parentheses, that's a reflection over the y-axis. So let's look and see what this actually does to the equation, okay? So if I replace the x in the absolute value parent function with x minus h, it would look like x minus h inside the absolute value bars. Same thing if it was plus h. Same thing if it was b times x. Again, it's occurring, oops, I missed my x. It's occurring in the absolute value bars. And same thing with a negative. So all of these changes are occurring within the absolute value bar. So that's our horizontal transformations. Now this bottom one here, we'll look at this practically here in a second, but just start to kind of think about the absolute value of a negative x and a reflection over the y and what kind of an effect that could have on this graph. All right, these next ones, these are going to be all the vertical changes. So again, just review from last class. This is a shift up, a shift down. If a is greater than 1, it's a vertical stretch. If a is between 0 and 1, it's a vertical compression. And this is a reflection over the x-axis. So again, what this is going to look like on the equation, we're taking the absolute value equation and we're adding k to it. We are taking the absolute value equation and we are subtracting k from it. We are multiplying it by a, or we are making it negative. So these changes all occur outside the absolute value bars. Now, if there are multiple transformations, this is the typical structure you're going to see. Now, what I want you to pay attention to there is that the b value, notice, is factored out from the x and the h where it might be touching it. So we need to make sure that if there's anything in front of the x that we factor it out. The reason for that is it makes this hk value very clear to see that that is the vertex of our graph. So that HK is going to be the vertex as long as we factor out the B. And that is going to be a similar pattern that we're going to use kind of throughout this year. All right, so let's look at some examples. Okay, the first thing we're going to do is we're going to determine the vertex. The vertex is the HK value based off of this structure of the function. So in this case, if it's x plus 1, then -1 is the x-coordinate, and 3 is the y-coordinate. Transformations, okay, we've gone left 1 and up 3. And then we're going to go ahead and sketch this graph. Well, this graph from the vertex is going to do the same thing that the parent function did. From the vertex, your parent function went right 1 and up 1. It went right 2 and up 2. It went left 1 and up 1, and left 2 and up 2. This is what the parent function did in relation to the vertex. So this graph is going to do the same thing. Right 1 up 1, right 2 up 2, left 1 up 1, and left 2 up 2. Now we'll look at a little shortcut for this here in a second, but this concept of seeing what the graph does from the vertex or from the 0, 0 point is something we're going to use on our other graphs throughout the year. All right, so domain is from -infinity to infinity, and the range of this graph is from 3 to infinity. All right, so let's go ahead and look at B. Again, the first thing we're going to do is find the vertex, finding that HK point. So in this case, that vertex is 3, 4. All right, transformations. This graph has a reflection over the x, a vertical stretch, and then obviously since our vertex moved, it's gone right 3 and up 4. So again, let's look and see what this graph does in relation to what the parent function does. So typically our parent function in relation to the vertex went right 1 and up 1, went right 2 and up 2, left 1 and up 1, and left 2 and up 2. That's what it did from the vertex. But this graph is going to look a little bit different because this graph has been both reflected over the x and vertically stretched. So that's going to affect the way this graph moves up and down in relation to the vertex. So because that is a value that we would multiply, because again, it's a stretch, compression, reflection, we're going to multiply those values by -2. And that's now how we're going to move from the vertex. So from the vertex, we'll go right 1 and down 2, right 2 and down 4, left 1 and down 2, and left 2 and down 4. So that gives me my new function. Now the reason we're able to do it this way is because the vertex was originally at 0, 0. And if you were to go ahead and multiply that -2 by that 0, 0 point, well, you're not really going to stretch 0, 0 because 0 times anything is still 0. So the only effect that our vertex could have is by a shift. So we can go ahead and shift that vertex wherever it is because again, multiplying it by anything is not going to actually affect that value. Now, like I said, there's a little bit of a shortcut with these absolute value graphs. So what I want you to look at is on this graph, basically we have a line coming off the vertex. Okay, look at the slope of that line that's coming off the vertex. Right, the slope of that line is that value that's out in front of the absolute value bar. So that's really the fastest way to graph these functions and how I'm going to graph the remaining ones. But I want you guys to see kind of how that pattern's affected because that's, again, the method we're going to use for each of these parent functions going forward. All right, so again, some characteristics. Domain is -infinity to infinity. That will be true for all of our absolute value functions. Range here, remember, we go bottom to top. So -infinity to 4 with a bracket. It is important that range is from the smallest value to the largest value. All right, let's go ahead and look at our next one. So again, let's find our vertex. So on this one, it's important to notice that this 3 value here is factored out. That makes it easier for us to see what our vertex is. Okay, we are still able to say that our vertex has an x-coordinate of 4 and a y-coordinate of -6. But before we get there, I want to look at how this graph is affected by some of the absolute value properties that are listed on your notes. So one of the properties that's listed there is that the absolute value of a times b is the same thing as the absolute value of a times the absolute value of b. Using that property, we can actually rewrite this equation to look like the one that we just did, because the absolute value of 3 times x minus 4 is going to be the same thing as the absolute value of 3 times the absolute value of x minus 4, which is just the same thing as 3 times the value of x minus 4. So that is the way that I can rewrite this equation to look like we just did. Again, makes it a lot easier to see where your vertex is. Okay, our vertex here is at 4, negative 6. And then we can go ahead and apply that same idea that we did in the previous one, where the number out in front is the slope coming off the vertex. So coming from the vertex, I'm going to go up 3, right 1, up 3, right 1. And then again, this graph does have symmetry, so I'll do the same thing on the other side to get that V shape. All right, transformations. Again, depending on at what point you're looking at, for this graph, a horizontal compression is going to look like a vertical stretch. Now, that is very unique to the absolute value function, just due to that real linear nature of the parent function. So you could write this as a vertical stretch. I'm going to go ahead and list it as a horizontal compression, just because that's the way it looked on the original function. So horizontal compression, and then we've gone right 4 and down 6. All right, more characteristic review and behavior. As x approaches negative infinity, f of x is approaching positive infinity. As x approaches positive infinity, f of x is approaching positive infinity. All right, looking at our next graph, finding our vertex. So before we do that, let's look at another property. Okay, it says that the absolute value of negative x is the same thing as x. And we know that's true. But applied in this case, I could rewrite this as 1/2. Two ways I could rewrite it. I could say, take that negative out and say the absolute value of negative 1 times the absolute value of x minus 2. And then using that same property, the absolute value of negative 1 is just 1. So essentially what's happening here, that negative is not just getting moved to the outside. That negative actually is disappearing, because the absolute value of a negative is the same thing as the absolute value of a positive. So I can rewrite this function as 1/2 absolute value of x minus 2 minus 1. Now again, this is pretty unique to absolute value, but essentially what that's saying is that reflection over the y is not going to change the way this graph looks. But the key thing to notice here is that that negative is already factored out of what else is inside the absolute value. If that's not the case, then you are going to need to factor it out in order to make that happen. All right, so let's go ahead and find the vertex. Again, looking at it this way or looking at it this way, we can see that the x-coordinate is 2 and the y-coordinate is negative 1. Transformations. This graph has a vertical compression. It does have a reflection over the y, even though it doesn't really have the effect in the shape of the graph. And we've gone right 2 and down 1. Let's go ahead and sketch our graph. It has a slope of 1/2, so up 1 over 2, up 1 over 2, and then we'll just reflect it on the other side. And then some more vocab review. So this graph is positive from negative infinity until the x value of 0, and then it picks back up at 4, and then it's negative from 0 to 4. All right, so now let's look at some where what's in front of that x is actually not factored out. So if that's the case, we have to do that first. It's very important that that is one of our first steps here. So I'm going to go ahead and factor this out. So I'm going to rewrite this as negative 2/3. And then if I were to factor out 2/3, this would be x minus 2 divided by 2/3, which is 2 times 3 over 2. Now that that value is factored out, then I can go ahead and take that 2/3 and move it to the front. I have to factor it out first. Notice I also factored it out before I found the x-coordinate of the vertex, because once I rewrite this, we can see a little bit more clearly that the x-coordinate of the vertex is 3. The y-coordinate here is 0 because there's no shifts up or down. But had I just looked here initially and said it was 2, all right, that would not be the x-coordinate of the vertex. One of the ways you can tell, the x-coordinate of the vertex should be the value that if you plug it back into the original, what's inside the absolute value bars becomes 0. And in this case, if I plug in 3, 2 minus 2 gives me 0. If I'd plugged in 3 based off of, if I'd plugged in 2 based off of the original, that wouldn't work. It wouldn't give me 0 in the absolute value bars. All right, so let me go ahead and rewrite this. And then we'll go ahead and graph it. So my vertex is 3, 0, and my slope is a negative 2/3. So down 2 and over 3, reflected on the other side. And I get my graph. Transformations, again, depending on at what point you write them, I'll go ahead and write them from the original. Reflection over the x, vertical compression, and we've shifted to the right. 2 or 3 depends on the order in which you apply those transformations. So I'll just say we shifted right. All right, this graph is increasing from negative infinity to 3, and it's decreasing from 3 to infinity. Again, some more vocab review from that first day. All right, if you feel comfortable, pause the video, try this next one. This is really combining kind of all those things here together. So first thing I'm going to do is I'm going to factor out the negative 2. So the negative 2 gets factored out. That leaves me with x plus 1. Okay, that is still inside those absolute value bars. And then I have the plus 1 over here. Now that that negative 2 is factored out, we can see the vertex a little bit more clearly. All right, that vertex is at negative 1, 1. What I also can do, though, is I can take that 2 and move it to the front. And remember, the negative does not move to the front because the absolute value of a negative is still just the regular same value. So that 2 can move to the front, so that would become 3 over 2. And the negative drops. So then again, depending at which point you write your transformations, I'll just write it from the original. We've got a vertical compression, a reflection over the y. We have a horizontal compression. We've got a shift. Again, now the shift depends on the order that you apply it in. So there's really more than one way you could write this. I'm going to go ahead and say just based off of the factoring out, it's gone and shifted to the left. But honestly, you could say it shifted right. It really just matters in what order you do those in. Basically, this graph has either gone right, then been reflected, or this graph has been reflected and then gone left. You can do either of those. It just depends on the order. Typically, though, I do think it's best to factor out that value first and then just look at the transformations based off that. And then we've also gone up 1. All right, so negative 1, 1 is my vertex. My slope after applying all of those changes is up 3 and right 2. Reflect it to the other side. And that gives me my graph. Domain for all absolute value is negative infinity to infinity. Range here, bottom to top, is 1 to infinity. All right, so now using what we know about absolute value, we're going to work backwards. Okay, we're going to try to write the equation of the graph. Now, based off those properties, there's actually 2 different ways you could write this graph. You could write it with a vertical stretch or compression, or you could write it with a horizontal stretch or compression. So in this case, it says to assume there is no horizontal stretch or compression. It's actually the easier way to write this. So what we'll do is we'll figure out, hey, what's the A value going to be out in front, and then where's my vertex? So this graph we can tell has gone right 3 and down 2. The vertex is at 3, negative 2. So that means that this graph is going to be the absolute value of x minus 3 minus 2. To find this value out in front, we're just going to look and see, hey, what's the slope coming off of the vertex? And we're going up 2 and over 1. So we have a 2 out in front. It should be positive because your graph is opening up. All right, if you feel comfortable, pause the video, try the next one. All right, this next one has not shifted left or right. The vertex still has an x-coordinate of 0. We'll go ahead and find the slope here. So we're going up 2 over 5. It is negative because it opens down. So this would be negative 2/5 out in front. And then a plus 4 on the outside because that vertex is at 0, 4. All right, we're going to do the same thing now, but we're going to write it assuming there is no vertical stretch or compression. Well, again, we still find the vertex first. The vertex is still at 1, 3. So this graph is going to be x minus 1 plus 3. And in this case, there is no stretch or compression. It follows the same pattern as the parent function. with the exception of the fact that it opens down. So we do have to have a negative out front. Now remember, if we were to put that negative on the inside, that would not have an effect on our graph. So that negative does have to be on the outside. All right, but let's look at this next one. This next one is going to have some sort of a stretch on it. So let's find our slope. I'm going up from the vertex. I'm going up 1, 2, 3, and over 1, 2, 3, 4. So it's got a slope of 3/4. Now again, we're not going to write this as a vertical stretch or compression. So what I'm going to do is I'm going to put it inside the parentheses. And if I know what that vertex is, it's at 4, I have to do it as x minus 4, or you could distribute it. But again, what we cannot do, this equation is not 3/4 x minus 4. We cannot write it that way because again, the x coordinate should be the value. If I plug it in for x, it makes the parentheses 0. And 4 in that current form would not work. Now, if you wanted to, you could write this as the absolute value of 3/4 x minus 3. Okay, that would work. Either of those is okay. They would both give you a correct answer. It's a matter of whatever preference you have. Again, there is no vertical stretch no vertical shift here, so we don't need to put anything over there on that side. So either of those equations is correct in this case. All right, so now the last thing we're going to do is just what we just did but with words instead of the graph. So we have an absolute value graph, okay, and we're going to take the parent function and we're going to apply these changes. So we're going to shift it right. So shifting it right would be x minus 3 in the parentheses. We're going to reflect it over the x-axis, so that's going to be a negative out in front. Then after we do that, we're going to shift it up 2. So the order that we apply these transformations in actually does matter. We need to think about what's actually happening here. So this is f of x minus 3. This is a negative f of x. After we've done those transformations, we are then going to shift this up 2. To shift this function up 2, we're going to take f of x and we're going to add 2. So I'm going to take the function that I have and I'm going to add 2. So that one's pretty straightforward. But occasionally, the order that we apply those transformations in can make this a little bit more difficult. So what we're going to do now, we'll start with a shift left 2. So a shift left 2 would be f of x plus 2. So this is going to become x plus 2. A shift up 4, that's f of x plus 4, so we can just put a plus 4 on the outside. What's a little bit different here, though, is the order in which we're applying these transformations. After we have done those two transformations, we are then going to do a vertical stretch. So what a vertical stretch is 2 times f of x. So what that means is I'm going to take the f of x function that I currently have and multiply it by 2. That doesn't mean to stick a 2 out in front. Okay, yes, that would have a vertical stretch, but it wouldn't happen after the shift up 4. If I'm multiplying the function by 2, I'm multiplying the whole function by 2, which means that what I have left is 2 times the absolute value of x plus 2 plus 8. All right, now let's look at this last one. A horizontal compression by a factor of 1/2. So what that means in terms of function notation, first of all, remember it's backwards. That's going to look like f of 2x. Okay, so what that would be then is the absolute value of 2x. Then we're going to have a shift down 2. So we're going to take the f of x function and we're going to subtract 2. So I'm going to do minus 2 at the end. All right, so that is it for absolute value graphs. Again, some of these concepts that we've seen here, we're going to continue to do with a new function in almost every unit that we see this year.